So today I'm going to talk about some work which we have been doing at the SNBNCBS National Center for Basic Sciences and also Bose Institute to Kolkata in collaboration with Dipankar Home, one of our ex-students Shiladitya Mal, who is presently at HRI, and two of our current students, Devarshi and Shorodhi. So first of all, if you look at the title, Sequential Sharing of Non-Local Correlations, what does it seem to you? How do we share non-local correlations? That's the whole point of the talk. And as we go on, we'll try to define what we exactly mean by sharing of non-local correlations. Okay, so this is the brief plan of the talk. First of all, as I said, I'm going to talk about the problem. What do we mean exactly by sharing of correlations, sequential correlations? And then here I would like to, just emphasize that in any problem where one shares correlations, you really have to, there has to be a trade-off between how much information you extract from a given measurement and to what precision you are actually doing the measurement. And the context for studying such kind of trade-off comes naturally within the framework of POVMs. So that we would talk of as we go on. And then in this talk, we would talk about this proof of impossibility of, say, violation of bell-type correlations as well as steering correlations by one party and two other parties who act on the other side sequentially and independently of each other. So this in a sense is the whole problem, so that we'll discuss the proof. And then as we go on, we would, some of you may be thinking, what is the whole business? Is this just an academic problem? Why do we need to study such sequential correlations? So we would like to emphasize that no, it's not just an academic issue. There can be interesting applications, and already there have been some experiments which have come up on this. And finally, after we talk of the CHSH, we would come to steering inequality. So that, in a sense, is the plan of the talk. Okay, so what do we mean by sharing of non-locality? So before we go to non-locality, let us first of all consider sharing of entanglement. And everybody knows that entanglement cannot be shared freely. So if you have an Alice and a Bob, for instance, then Alice, the entanglement is monogamous. So if you have a tripartite state between Alice, Bob and some Charlie, so you can see that Alice can be at a time maximally entangled with either Bob or Charlie. Otherwise, no signaling is violated. But this is in the context of a tripartite state. You can imagine another scenario when Alice gets sequentially entangled with Bob and Charlie. Okay, so all the time there is a bipartite state, but one party, say Bob, performs a weak measurement, and then subsequently Charlie can perform another measurement, and you can see that no signaling is not applicable in this situation. Why? Because we are talking of sequential measurements. So again, you can look at this cartoon. For example, you have Alice and Bob at T1 sharing a certain state, and then at the further instance, when rho AC is conditioned by Bob's measurement, Alice gets entangled with Charlie. So this is the sort of scenario that we would be discussing in the present context. Okay, so here is the whole essence, sharing of non-local correlations sequentially. So the question one asks is that, how does one reveal non-locality between Alice on one side and sequence of Bobs on the other side? And how do you address this question? Of course, you address this by considering various forms of non-locality. First of all, you can consider Bell violation between different pairs, Alice Bob 1, Alice Bob 2, so on and so forth, Alice Bob n. And you could also consider other forms of non-locality, not just Bell violation, but steering type of non-locality, so on and so forth. But all the time you must remember that if your first Bob performs a strong or sharp measurement, then no correlation remains. Okay. So you have to ensure that up to the n-1th Bob, all of them must perform weak measurements or POVMs, unsharp measurements. Okay. Otherwise, no entangled state remains for the subsequent nth Bob. So this is the scenario, this is the setting, and pictorially actually you can represent it like this. And this question, in my knowledge, was first addressed or attempted to be addressed by Jisa and collaborators in a PRL in 2015, and they talked about it in the context of CHSH violation. And they tried to see that how many Bobs on the other wing can violate a Bell type inequality, CHSH inequality, with Alice on the one side. So as you can see that various Bobs perform measurements at instances T1, T2, so on and so forth. And they gave a numerical conjecture that taking a model of a measurement that not more than two bobs can share such non-local correlations. In the work that I'm going to say, that we have actually found a very simple analytical proof of this relation. And as I'm going to say, that this is not just an academic question, because some of you may be aware of some works on unbounded random certification in Nature, Pironi et al. In 2010, and more recently by Kirchhoff et al. They actually use this formalism of sequential measurements, okay, sequential sharing of correlations. But let me be very clear, in this present work I will not be talking any bit about any applications. We will just formally address this problem as to how many bobs can share such non-locality. Okay, so now let us be even more specific. Let us come to the context of just restrict ourselves to an entangled pair of spin-half particles. And Alice has access to one of these particles of the pair, and series of bobs on the other side are there who can access the particles sequentially but independently of each other. Okay, so again, as I said, no signaling is certainly not applicable in this scenario. And Alice, of course, performs a projective measurement which has dichotomic inputs and outputs, 0 and 1, because we are just dealing with a qubit spin-half particle. And the series of bobs up to the last but one bob perform one parameter POVM. So again, we are restricting to a very simple scenario. One parameter POVM, again with dichotomic input and output, while the last bob may always perform a projective measurement. Okay. And something else which also is important here is that we assume unbiased input settings for Alice and all bobs. And what does it mean is that the frequency of receiving either input 0 or input 1 is the same. There is no biasness at input. So in this context, this can be pictorially represented like this. Alice and Bob share a spin-half entangled particle, and then sequentially subsequent n bobs can access this particle independently of each other without any biasing of measurement inputs. Okay, so how do we proceed first? Okay, we see, for example, we take the CHSH inequality and we check that for how many pairs is it violated. Alice, Bob 1, Bob 2, so on and so forth. And this, as I said, upper limit of 2 bobs was conjectured numerically for unbiased settings by Gisa, Popescu and collaborators. And how did they do it? They constructed models of measurement apparatus in order to do so. However, we claim here that a very simple proof of this analytically can be obtained if we just consider a one parameter POVM. And in this context of one parameter POVMs, the information gain versus disturbance trade-off emerges naturally. And this again advertises the utility of the POVM formalism or unsharp measurement formalism. Okay, so this is just a repetition of the slide, so let me just skip it. And again, this is a repetition. We ask the question, how many such bobs can be there who can violate CHSH with Alice on the other side? Okay, so as I said, POVMs provide optimality in the trade-off between information gain and disturbance. So this aspect is clear. Bob 1 has to extract some information, otherwise no CHSH can be violated. But the amount of information that Bob 1 can extract should also be limited, otherwise there will be no correlation which remains for the subsequent Bob. Right, okay. So how does one deal with it? For example, this very simple POVM formalism. So we can take a system state, which is a qubit state, and another apparatus state, which is represented by phi q. Now, which is elementary, measurement, formalism. So joint system apparatus state can be written like this. So 0 couples with q minus 1. These are distinguishable apparatus states. Otherwise, you cannot extract any information. And the reduced system, of course, can be written like this, where pi plus pi minus are the usual projectors. So now in this context, if your measurement is not a sharp one, one can define something called a quality factor. If you can look into it, this just represents the overlap between two distinguishable apparatus settings, that is q plus 1 and q minus 1. One which one obtains if the outcome is 0, other which one obtains if the outcome is 1. So now if the distinction or distinguishability is perfect, then of course this is an orthogonal, these two are orthogonal, so you get quality factor at 0. And in a complementary scenario, you can also define something which is called the precision of measurement, which actually takes into account the total spread of the apparatus wave function, and g equal to 1 corresponds to a sharp measurement. If you can write down your probability of outcomes in terms of g, you can immediately see that if g equal to 1, this is just a sharp measurement defined in terms of pi plus pi minus, which are the usual spin-half projectors. Now the question is that how are G and F related? Okay, you can immediately see that they are in a certain sense complementary. If you increase G, then F is reduced. If G is 1, then F is 0. But is their relation linear or is it nonlinear? Remember, the whole idea is to extract maximal possible information with minimum possible disturbance on the state. So how does one actually relate G and F? This is the question which in fact was addressed by Jisa and others in their PRL of 2015, and for that they actually gave some models of apparatus, and using some numerical procedures they obtained a certain kind of relation connecting G and F. However, this is just a back of an envelope calculation to see that if you apply one parameter POVMs, then the relation between F and G emerges very naturally, and this is an optimal relation. To repeat, so what is the optimality condition? It actually talks of the best trade-off or largest precision G for a given quality factor. Now you see, you can write down the unsharp measurement with the effect parameter E plus minus lambda, and after pre-measurement in terms of the usual Luder transformation, your transform state rho prime takes this value, and lambda represents the parameter of sharpness or unsharpness. Now you can again write the probabilities of outcome P plus minus. Now they are written in terms of this lambda. Now if you compare this lambda with your previous result, that is this one, okay, P plus minus written in terms of G with P plus minus written in terms of lambda, you immediately see now that a relation between G, F and lambda emerges. Lambda is nothing but G and F is nothing but 1 minus lambda square, and thereby therefore a relation between F and G emerges, and this is of course the most optimal relation which was derived numerically by Jisa, Popescu and others, which emerges very simply in the context of one parameter POVMs. And again, to check in the limit of sharp measurements, you get G equal to lambda equal to 1, F equal to 0, and vice versa. So what we have is that this one parameter POVM formalism enables us to immediately derive an optimality condition between these two objects F and G. Okay, so this is the whole essence of the problem. So now once you have it, you can immediately apply to the context of spin-off particles shared by Alice and a series of bobs on the other way. Okay, so this is the scenario as we consider, and first let us address the Bell CHS formalism. So let us choose Alice's settings to be very simple, X and Z, and let us choose Bob's settings to be one which achieves the Tyrrellson's bound. And you see now, if you apply the one parameter POVMs by the n-1 Bobs with no bias, that is input, all these inputs X, Y1, Y2, etc. occur with equal frequency, 0 and 1 occur with equal frequency. And then you just calculate the joint probability of getting outcome by A by Alice and Bn by the nth Bob, and the measurement by the subsequent Bob, the state that the subsequent Bob accesses is conditioned by the earlier Bob. And then in case of two Bobs, you can write the joint probability. Again, I mean, this is a very old result. This was first actually written down by Paul Bush in the 1980s. So you obtain the CHSS factor 2 root 2 times lambda 1, and immediately you can see if lambda 1 greater than 1 by root 2, you get CHSS violation. Now if you take more Bobs, for example, if you take another Bob, then the second Bob measures sharply, you have the CHSS factor between Alice and Bob 2, again given in terms of lambda. Now you have to find a range for lambda where both Bob 1 and Bob 2 violate CHSH with Alice, and this is the range where, I mean, both of them can indeed obtain CHSH violation with a single Alice. So this is again a very simple result. Now the question is that you can obtain this, what if we have more than two Bobs on the other side? So you can again exactly do the same thing. So instead of two Bobs, you can take three Bobs. So in this case, the first and the second Bob measure weakly, whereas the third Bob measures sharply. So again, you can write down the joint probability CHSH correlation between Alice and Bob 3. So here is the CHSH C3 factor. Now just remember one thing, the third Bob is unaware about the inputs of the previous Bobs. So when we are writing C3, we have to average over all the previous inputs. So this is the average correlations between Alice and Bob 3. So you do it, average CHSH between Alice and Bob 3, and now you have three expressions. You have I3, that means average correlations between Alice and Bob 3, and of course you already have Alice Bob 1 and Alice Bob 2. Now you ask the question whether you can choose any lambda, and by the choice of any lambda 1 and lambda 2, which will enable you to obtain all three CHSH violations. Is that possible? Of course, this is certainly not possible. You can convince yourself that, for example, you could take various values. I've just written down one example. In this, you can never obtain a scenario when all the three bobs can independently and sequentially achieve CHSH violation with Alice on one side. So what does it tell us? Not more than two bobs can share non-locality defined in terms of CHSH violation with Alice on another wing. Okay, so this is a sort of result that we derive. So how does it look? Okay, sorry, I think probably, okay. So in this thing, of course, when I said that I chose a particular type of measurement settings, which gives the Tillotson bound. Now somebody can ask the question, well, Tillotson bound is obtained in the context of sharp measurements, but now I'm trying to see whether using weak measurements, many different bobs can violate CHSH. So what is so special about that? The measurement setting. You can in general choose any other type of measurement settings. Actually, this question was asked by the referee of this work. So we actually then we did some more calculations. We actually, chose general settings, non-orthogonal settings, and did the same problem. This is just a little more algebra. I don't think physically you obtain anything else, but for completion, you can just state the result. Again, you can do the same thing, Alice with Bob 1, Bob 2, and Bob 3. And again, you can see that even with generalized measurement settings, you get no improvement in the violation. The result remains intact, that not more than two bobs can obtain CHSH violation with Alice on the other wing. And this is the scenario. So you see, to summarize in a nutshell, Alice is on one side who makes a strong measurement, and there are sequential bobs on the other side who make, and two of them can make weak measurement, one of them can get a strong measurement. And this result holds irrespective of which of the bobs can perform a strong measurement. For instance, if these two bobs can perform weak measurements, you do not get CHSH violation between Alice and Bob 3. And you can also interchange. For example, you can obtain CHSH violation with Alice Bob 1 and Alice Bob 3. You don't get it with Bob 1 and Bob 2, Alice and Bob 2, so on and so forth. So this is one particular result. Now, as I said that, why is it interesting? Are people at all interested in finding out? Of course they are. People who do real experiments. For example, this is a subsequent experimental work which came out after a paper. And there they have actually addressed this question, trying to obtain CHSH violation by Alice and at least two bobs. And this is a group in Italy, and here is their setup. So you can see Alice, first bob, and conditioned on first bob's measurement. This is the second bob. And this is the CHSH violation. So one of them is represented by red. That shows the I1, okay? CHSH factor between Alice and the first bob. This is the CHSH blue, Alice and second bob. And you can see that there is a region of parameter space where your Bell violation in both cases exceeds 2. So you can indeed obtain CHSH violation. So this was work done by one group. There was also a Chinese group which repeated the same experiment, okay, using their setup. And they have also obtained a similar violation of CHSS, that is sharing of non-locality with multiple observers with one entangled pair via optical weak measurements. Okay. So these are some of the experimental results which have considered CHSH violation. So how am I doing with time? Maybe I think I have 5 more minutes. Okay. So now let me come to the other part of this problem. So far we have just talked about sharing of non-locality in terms of CHSH violation. Of course, non-locality is not restricted by just Bell CHSH violation. There can be other forms of non-locality, especially weaker forms of non-locality. I started by talking about sharing of entanglement. Then I went on to sharing of Bell non-locality. However, as most of you know, there is also an intermediate form of correlations. So this is a weaker form of non-locality compared to Bell violation. And all Bell violating states are a strict subset of steerable states. That was indeed shown by Wiseman and co-workers. I don't see him here, in a 2007 paper. So they showed that Bell violating states form a strict subset of all steerable states, which in turn form a strict subset of all entangled states. So of course, steering also corresponds to a form of non-locality which can be, perhaps easier to implement in experiments. And this is enabled these days for formulation of one-sided device-independent key distribution protocol. So now we can ask the same question in the context of steerability. Can we actually, show that, for example, are the number of bobs limited who can share steerable correlations with Alice on the other wing. Or in other words, this is the question that one poses: how many bobs who act again sequentially and independently of each other, who can steer Alice's state on the other side? And then, of course, as we were using the Bell-CHSH inequality in the earlier formalism, so now we can use the analog steering inequality, again, which was formulated by these people, Cavalcanti, Fura, and Weizmann in 2015. So in this 2 cross 2 cross 2 scenario, that is 2 qubit, 2 parties and 2 measurements, this forms a necessary and sufficient condition for steering. So we immediately apply this inequality in the context of this problem when we are dealing with 2 qubits and 2 measurement settings for per party and 2 parties. So we repeat the same exercise, and before going that, there are some other works also. We also need to know what is the condition on the quantum state such that it violates this CFFW inequality. And here also there have been subsequent works by Cavalcanti, Kwan et al., and we have also done some work here. So which actually find this condition, which is, analogous to the Horodecky condition for Bell violation, that given a quantum state, when will it violate the CFFW inequality? Again, you can do exactly as Horodecky et al. Did with Bell violation, CHSH violation. You can write a correlation matrix, define some coefficients, and then this function S is defined like this in terms of eigenvalues of the correlation matrix. V and V tilde are the 2 largest eigenvalues, and if your S rho greater than 1, then your steering inequality is necessarily violated. And subsequently, there are also some interesting monogamy results for steering, but which is not relevant for the present discussion. So using these results, we actually apply in the context of our problem, the violation of CFFW inequality by Alice and 2 bobs. And what do we here? Again, we choose some particular most general settings, and we first of all obtain the correlation between Alice and Bob using the Sun-Sharp parameter lambda 1. And then with the condition state, which is after Bob 1's measurement, we write down the average correlation between Alice and Bob 2. And here also we obtain this correlation function S2. And then we apply the necessary and sufficient condition for steering by the 3rd Bob. And here also one obtains that steering is not possible by more than 2 Bobs. So the result that was valid in the context of CHSH non-locality also seems to remain in place with a weaker form of non-locality, which is given by steering. Some of you may find it a little bit counterintuitive, because after all, we are talking of steering, which is strictly a weaker form of non-locality. Can't we increase the number of Bobs? So that question we also thought maybe it is possible. Maybe what we are doing, we are applying too much of a strict condition for steering. So we can go a little bit ahead. So instead of that, instead of restricting ourselves to just 2 settings, we can talk of a 3 settings scenario. Okay. Again, there is another n settings most generalized inequality which was proposed by these people in 2009. But there is a catch here. This is not a necessary and sufficient condition. Okay. So violation of this guarantees that there is indeed steering. However, vice versa is not true. So again, we can do the same exercise in the context of this inequality. And the advantage that we get here is that we can find that there is another Bob. Okay, now you can increase, if you do a 3 settings inequality, you can have 3 Bobs who can steer Alice on the other side. So if you increase the number of settings, then you can obtain another Bob who can actually steer Alice's state. Of course, this lets one ask the question, suppose if one keeps on increasing the number of settings, will we get sequential violation by more and more Bobs? So that's an open question. One can only conjecture that indeed this will be true, but the proof of this remains to be done. Okay, so I'm almost at the end of this talk. So this is the summary. So in this series of works, we answer this question, which was first posed by these people, Gisa, Popescu, and collaborators, that with how many sequential Bobs can Alice obtain CHSH violation? They asked the question in the context of CHSH violation. And what we show, they actually, as I've been repeating again and again, they actually address this problem in the context of, some would say, some contrived models of measurement operators, but you don't have to work that hard. You can just analyze this in context of POVMs, which actually gives you a nice trade-off between information gain and disturbance in a measurement which is optimized by a 1-parameter POVM. And applying this formalism, we show that analysts who measure sharply on one side cannot obtain CHSH violation with more than 2 Bobs on the other side. And this result, of course, is only valid for unbiased measurement settings. What happens for bias measurement settings may be a different question altogether. And then we of course also include more general, in fact non-orthogonal measurement settings. We see that no advantage is gained by using non-orthogonal measurement settings. And then what we do is we repeat the same question, not in the context of Bell violation, but in the context of steerability. And here we also show that sharing of steerability by Alice on 2 bobs using the CFFW inequality, which is a necessary and sufficient condition in the 2-2-2 scenario. This is not possible by more than 2 bobs and Alice on the other side. However, if you increase the number of settings on one side, okay, if you for example go to a 3 settings inequality, then you can still see that steerability is indeed possible by more observers. However, as I should again repeat, this is not a necessary and sufficient condition for the n settings inequality. And of course, I have no time to tell you, but indeed this is, let me emphasize, not just an academic exercise. Those of you who talk of device independent QKD should immediately realize that when we apply Bell violation to check the security of QKD, you can envisage a scenario when there is Alice and Bob and they actually check that Bell violation remains intact, but there could be a Charlie in the middle who has accessed this state at some earlier time and extracted some information. Still, Alice and Bob will obtain Bell violation. So one would think that security is there, but some information could have been actually extracted out by Charlie in the middle. So this is of relevance in QKD. And also there is another immediate area, randomness certification, where people have been trying to apply this formalism of sequential entanglement sharing. And finally, there are several other open questions which one would like to address in subsequent works. So what happens, I have talked of very particular kinds of non-local inequalities, CHSH for the Bell scenario, 2 particular inequalities for steering. What happens if we consider other types of steering inequalities? And also we could generalize the problem. So I had an asymmetric setup, Alice on one side and a series of Bobs on other. What happens, for example, if I have more Alices on this side and more Bobs? So these are some of the questions. And again, you can increase it as Arvind was trying to advertise Q-trits and things like that in the talk in the morning. What happens? Do we gain any advantage by taking higher dimensional states? Thank you very much.
So for 2-qubit states and CSH inequality, the magic number in some sense is 2. That you can, I mean, Alice can have correlation with at most 2 sequential Bobs. Now, for suppose you have a Q-trit system, 2 Q-trit systems, and then you look at the CGLMP inequality. So do you expect that magic number 2 to go up or go down, or do you have any intuition regarding that?
See, I have very pure intuition. I don't expect anything. Why don't you do this problem? It's very simple. Sure. So that's why I said this is one of the open areas which one can do for Q-tits or things like that. Yeah, sure. I think there's a question there too. Yeah, maybe you were first.
Should be a quick question, but at the first part of your talk with the CHSH inequality, have you thought of extending that to a CH inequality and looking at that?
Yeah, you see, I mean, we can think of many things, but we have to do that. I mean, of course, that's an idea. As I said, one can increase it to many other forms of inequalities.
One last question.
Hi. Thanks for that. With respect to your open question about the number of steering parties that could, I think the answer is probably that it can be arbitrarily large, but I think you would have to consider a more general measurement than you have been considering. So maybe it's something we can talk about after.
Yeah, sure. The only, hindrance to that kind of program I find is that there is no necessary and sufficient condition. You can of course obtain violation, but how can you be sure that you will obtain it in the most general scenario? I mean, you can of course have more settings inequality, more number of more generalized observations. But unless you have a necessary and sufficient conditions, along the lines of one that was proposed by you for a 2-2-2 scenario, I don't know whether you can be at all sure whether you are actually, addressing this question to its complete satisfaction. Thank you.
So let's thank the speaker.